Quantum interpretations are different readings of the same physics of quantum mechanics. There are some atoms to bring the consequences of the quantum theory in the level of compatibility with a human being's common sense. Dr. Wilson today will bring us to the exotic realm of Everettian quantum mechanics, or many words interpretation of quantum mechanics. He did his education in the University of Oxford and had some periods in the University of Monash in Australia before joining Birmingham in 2012. He's interested, as I know, in the metaphysics and philosophy of science, and he had some rigorous work on metaphysics of Everettian quantum mechanics, and lots of works on laws of nature, chance, probability, causation, and counterfactual. So it's a pleasure for us to hear your words. Thank you.
Thank you. So I don't know whether you can all hear me. I've had a sore throat recently, so I may lower the volume over the course of the talk, so do say if you can't hear me properly. So as Sahar alluded to, I'm essentially a metaphysician, but I did my doctoral work with Simon Saunders and David Wallace in Oxford, working on the metaphysics that can best be combined with the kind of many worlds interpretation or Everettian interpretation of quantum mechanics that they've been developing, that in some quarters known as the Oxford Everett interpretation, associated in particular with David Deutsch, Simon Saunders, David Wallace, Hilary Greaves, and as the name suggests, it's very popular in Oxford. Indeed, it's orthodoxy there to the extent that people joke there's something in the water. And I have indeed been turned into an Everettian during my time there. So, what is Everettian quantum mechanics? People like David and Simon like to say that it's not anything other than straightforward quantum mechanics. The Everettian picture is what you get if you take quantum mechanics literally, without changing it in any way. And in that sense, it's just an instance of scientific realism as applied to quantum mechanics. Scientific realism in general says that when you have a successful scientific theory, you should try and take it literally, you should look at what it says there is, you should look at what it says what there is does, and then you should, if necessary, do whatever interpretive work is required to connect that to recover the manifest image, so-called, the kind of world that we see and experience around us. As a version of realism, it's the most conservative version. You might be surprised to hear me say that. So I say it's conservative, not because it doesn't have many worlds in it, it does. It's conservative because it's not changing the physics in any way. When I say the physics, what I mean is basic linear quantum mechanics. So quantum mechanics without any kind of collapse rule, any kind of special second non-linear process that goes on during collapse events, takes over from the normal linear unitary quantum evolution. And it's conservative in that sense, it's not adding anything to the basic physics. It's not conservative in the sense that it doesn't postulate a lot of things. It postulates a lot of people living in a lot of worlds. And whether or not that kind of cost is an acceptable cost is one that's still very, very much up for grabs. But what I'm more interested in today is the issue about what it would take to make Everettian quantum mechanics coherent. Because a lot of people are initially tempted by the idea of getting rid of collapse and all the associated problems is a very attractive one. For example, as Chris was just describing, these issues about causation and non-locality look much less threatening in an Everettian picture, precisely because it lacks any analogue of, well, it lacks any specific collapse rule, which is what would potentially the culprit in generating the conflict with relativity. So that's one reason for one to like it, but there are many. Two other alternative approaches, briefly, that we haven't had much discussion, just to put them on the table. There's a hidden variables approach associated with David Bohm, but there are other versions of it than Bohm theory, which posit additional physical facts not captured by the quantum state. And those facts determine measurement outcomes. That kind of theory can be a deterministic theory. We may not in practice be able to predict what outcomes we're going to see, but nonetheless, the deep microphysics of the world makes those outcomes inevitable. And there's a special reason why they're unpredictable in principle. So that kind of approach adds things to quantum mechanics. It adds the hidden variables. If your Bohm adds corpuscles, particles with particular trajectories, and those trajectories aren't anywhere in the wave function. This is extra stuff that's being added to solve a conceptual problem. Similarly, there are these so-called dynamical collapse theories, and the GRW theory is the most popular of these. But again, there are more sophisticated versions. It's the most prominent of them, but there are more sophisticated versions. And what those do is add a dynamical collapse rule. They don't try and interpret collapse in the way that Hans was suggesting. Instead, they add collapse as a genuine physical process, just like wave function evolution, that's been going on, that had nothing special to do with minds. It's just been going on. Every now and then there are spontaneous dynamical collapses. And again, that's adding something to basic quantum theory. It's adding this collapse mechanism in. So in either way, so again, here's something that's being added to the basic physics in order to solve an apparent conceptual problem. And the Everettian project is to try and solve that conceptual problem without adding anything to the physics. And that's a big project. I mean, it is a project that needs to be, that's partly within physics. Decoherence theory is a very big part of making Everettian quantum mechanics coherent. But it's also a problem for philosophers. And in particular, philosophical conceptions of probability and possibility get called into question by, well, we need to look closely at our notions of probability, possibility, and necessity if we want to provide a convincing Everettian worldview. So I'm going to describe this as the Everettian explanatory project. So the project is, take quantum mechanics literally, using just the resources in simple unitary quantum mechanics, explain how the world we see around us emerges. And one of the distinctive features of the Oxford-Everettian route to doing this is to appeal to a notion of fundamentality. And it's, so you have the fundamental level and you have the non-fundamental level. And insofar as there's interesting things going on at the non-fundamental level, we can say that there's emergent phenomena. And the central claim of the Oxford-Everettians is that fundamentally there's just the quantum state. But nonetheless, we also, out of that quantum state emerges a whole collection of universes, each of which is like this one. So it's a kind of Copernican term in quantum mechanics. It's not that there's some special collapse mechanism that is explaining why there's just this one history, and we see just one history. Rather, there are many histories, and the fact that explaining why we see one is just that we are only in one. There's nothing special about this history, this universe, this course of events. Rather, there are many courses of events turn out differently, and they're just somewhere else, causally and/or spatio-temporally isolated from the world, the universe that we ourselves are in. That's a sketch of the large-scale Everettian project. What I want to talk about today in particular is the contributions that I think metaphysics, or as some people call the kind of metaphysics I'm talking about, analytic metaphysics, can make to this explanatory project. Now, analytic metaphysics has got a bit of a bad press recently, and not without good reason at times. So there's been, Hans mentioned the kind of positivist turn at the start of the 20th century. Metaphysics was object of hate for the positivists, but philosophers would say we got over that. That was a kind of period of philosophical immaturity, and now we're recognising there is scope to do genuine metaphysics. The problem is metaphysics is hard, and there is quite a lot of bad metaphysics out there. And this is true of many fields. There's a lot of bad physics out there probably too. But metaphysics being less tied to experiment, tied to predictions, it's harder to spot and weed out bad philosophy than it is to spot and weed out bad physics, generally. And we're going to hear, I think, after lunch from James Ladyman, and if I know James and judging by the types of his talk, he's going to have some rather negative things to say about analytic metaphysics. I do intend to be doing what he would categorise as the good kind of metaphysics, that is, metaphysics that takes proper account of science. And I think one of the things that can best bolster our confidence that metaphysics is in fact a respectable discipline with that can have some hope of attaining knowledge of facts. It's going to have to be able to engage with science, and insofar as it can fruitfully engage with science and indeed bring ideas into science that are useful, that reflects well on metaphysics and tells against these kind of very general positivist style complaints about it. Okay, so I'm going to talk about two ways that metaphysics can help the Everettian project. They're both kind of related to probability. Probability has often been thought to be a really big problem for the Everettian approach, and I'm going to suggest some ways which arguments and theories which have come up independently in metaphysics over the last 20 or 30 years, 40 years maybe, can be used by the Everettian to help with the explanatory project. The project, remember, of explaining how the world we see around us emerges from the fundamental quantum state. So, okay, so the first question. Do we, in Everettian quantum mechanics, have a case of parallel universes or splitting universes? Now, these are two metaphors that both get thrown around a lot, and it's bizarre that they should be thrown around so much without people noting that they're incompatible pictures. We either have universes that either parallel or they split. They can't be both. Here's a picture. It's one or the other, I say. So let's try and hash this out in a little bit more precise way. I'm not a physicist. I'm not going to try and explain any physics in anything like the kind of detail that we had in the first few talks. This is just a formalism, a way of writing quantum mechanics that's particularly congenial to Everettians. It was developed in the context of quantum cosmology when we wanted to describe the quantum states of whole universes. So one problem with doing cosmology using quantum mechanics under the ordinary so-called orthodox interpretations is that if you are trying to look at the quantum states of the whole universe, there's no observer outside, you might think, who's able to collapse the state or able to observe the whole quantum state of the universe. And so any theory which has observation as a central feature in it is going to have problems when it's applied to the entire universe with no outside observer. So this kind of formalism was designed to make that kind of application of quantum mechanics and cosmology go more smoothly. So I'm not going to explain the physics, but what you get are these histories, CA, and you can characterize certain conditions, which I haven't written down, on sets of those histories. And those conditions can be thought of as, well, it's called various kinds of decoherence conditions. but they can be thought of as not kind of effective non-interference conditions. So if you have many histories and they're not interfering with each other, you can consider them as effectively dynamically isolated from one another, approximately isolated, if not completely causally isolated. Then any set of histories meeting a condition like that gets called a decoherent history space. And I'm going to use this technical term, this is my technical term, ever world, to mean whatever it is that gets represented by an individual history that is a member of a decoherent history space. That is, any history which is a member of a set which meets the decoherence condition of effective dynamical isolation. So whatever one of those objects is like, we're taking this formalism to be representational. So it represents something, whatever it represents is an ever world. And it's up to the everything to explain why those things deserve the title world. So they say, we've got a history, and our world is just one of the things that is described by one such history. And those other worlds have other people in, and they're just as real as we are. It's just that they're in that world, we're in our world, and so we don't get to talk to each other. So what are these Everett worlds actually like? Do they overlap or do they diverge? So the picture should hopefully make it very clear. Whether or not that initial segment is something which the two histories actually have in common with one another, like two rail routes that share track for a while, but then become apart. Those routes have some track in common. Here, according to overlap, the worlds literally have initial segments in common. Whereas in divergence, they don't have initial segments in common. Those initial segments on the in the right-hand picture are meant to be qualitatively indiscernible from one another. The word identical can be confusing here, because identical in English is ambiguous between qualitatively indiscernible, having all the same properties as, and being one and the same thing as, being even philosophers can sometimes say being numerically identical to. So I'm going to use this distinction. Are the initial segments of two Everett worlds, are they merely qualitatively indiscernible from each other, as in divergence, or are they really one and the same, as in overlap? And as a metaphysician, as a realist metaphysician, is trying to take these things literally as far as possible. And obviously you can take things too literally, and perhaps that's a mistake I'm making, and perhaps you can try and persuade me of that afterwards. But taking things literally, it's either one or the other, the way these worlds are. They either have parts in common or they don't. So, how can we adjudicate between these? It's going to depend on, I think, a fairly subtle point of metaphysics. It's going to depend on the way in which we take the projection operators to represent. I want to say that point of metaphysics is actually independent of the physics. So, here's how it goes. We have two histories here, and the way it's written is kind of confusing because it goes right to left. So actually the most recent time, the latest time is Tn. T0 is the first time. So we're taking a history running from T0 to Tn. And then we stipulate that we've got a pair of histories where those projection operators are the same for everything except the time n. So we have these histories constructed from the same projection operators, but are the entities that are represented these, you might think of them as property instantiation. So I should have said, you can think of each of these P's as a property that the whole universe that a whole universe has at a time. So then, my claim is going to be that whether the entities that are represented by these things in the one history are numerically identical. So looking at these ones where the projection operators are equal, the question is, are these things that they're representing merely qualitatively indiscernible or actually numerically identical. And if you take these projection operators to represent what philosophers call token property instantiations, individual instantiations of a property, particular instantiations, then you're going to get overlap, because these different projection operators in different histories before they come apart are going to be representing one and the same token. But we can also think of these projection operators, I'll leave this up now, as representing types of property instantiation. So in that case, we could think of these histories as saying the first instance is of this type, the first instance is of this type, the second instance is of that type, and so on. And that doesn't bear any commitment to two entities, two property instantiations can be of the same type without being one and the same. And so if we interpret these projection operators representing types of property instantiation rather than representing individual property instantiations, then this formalism is fully compatible with the diverging picture. And this is going to be the claim. The physics itself doesn't determine whether or not we should interpret these strings of symbols here as representing overlapping worlds or as representing diverging worlds. Rather, that's something that metaphysics is going to have to answer for us. And it turns out that there are reasons from within metaphysics for preferring a diverging option. And so I'm going to describe an argument given by David Lewis. And by the way, I should have said at the start, there was a handout for this talk. It didn't get printed, or there may have been some printed, but it's unclear where they ended up. So if you have one, that's great. If you don't, then it was emailed around, so if you can bring it up on your laptop, that's also great. If you don't have either the printout or the laptop, then I apologise, but it should be in your email account somewhere. So you can go back and look for it later. So David Lewis, he wasn't thinking about quantum mechanics. I'm going to turn this off first, stop it being distracting. He wasn't thinking about quantum mechanics, but he was thinking about multiple universes. Because David Lewis had a theory of possibility, a theory about what it was for something to be possible that appealed to the existence of many worlds like ours. So he thought, we live in one world, things could have been different, and what it is for things to have possibly been different is for there to be some world somewhere else where they are different. So every possibility is realised, and it's realised in just the same way that this possibility is realised. It's just we're in this one. So he had a purely philosophically motivated picture, which was in some ways quite similar to the Everettian picture. And I've actually, in other work, I've argued that these pictures are a lot closer, or can be brought a lot closer together than most philosophers have thought they can. So here's his argument. He says overlap, where the world genuinely split, it makes nonsense of our thought and talk about the future. So we ordinarily think there will be a future. We wonder about what will happen to us. And if we are on the overlap side, and we're before the split, then there's no sense in wondering what will happen, left or right, because both of them are going to happen. Both of them lie futurewards of you, you might say. So given overlap, thinking about the past, there's one unique past, but there's many futures of your segment. So we can't wonder about what the future will hold. We know that it will hold many different histories, but as long as we know the range of possible histories that lie to our future, we can't wonder about which of them there will be, because there'll be all of them. So, without going into, did I start on time or at 42? Okay. I'm going to try and go to 1/2 past. I hope that's okay. So, what overlap says about the future is that what will happen is, probably the best thing you can say about the future, given overlap, is that what will happen becomes relative to a history, or history dependent. So, you might say if you're about to do a spin measurement, and you're an Everettian, you can't wonder what will happen. There'll be a branch with up and a branch with down. So relative to the up branch, the experiment will come out up. Relative to the down branch, it will come out down. And you can try and say that, but I don't think it works. David Lewis doesn't think it works, because we don't. When we worry about the future, when we have hopes or fears for the future, those hopes and fears aren't relativized to a branch. It's not that we kind of hope that relative to the up branch, it'll come out up. That would be absurd. Relative to the up branch, it will definitely come out up. You can't hope that it will come out down and down branch. The down branch will definitely come out down. And so it seems like there's nothing there to hope or fear in the future. We can't hope that it will come up, or hope that it will come out down, because we just know for sure it's going to come out both. And that seems to David Lewis, it seems to me, to do some serious damage to our normal thoughts about the future. But you don't get that problem in divergence, because right now we're either in one branch or the other. We just don't know. We're either in one history, we're either in one world, sorry, or we're in the other. We just don't know which. And if we're in the left-hand one, then say the experiment's going to come out spin up. If we're in the right-hand one, it's going to come out spin down. So there, now we have on the right-hand side, in the divergent picture, we have a subject matter for our uncertainty about the future, for our hopes and fears about the future. We can hope that we're in the left-hand world rather than the right-hand world. We can fear that we're in the right-hand world rather than the left. And if we're at a position in that world before the quantitative divergence occurs, then we're going to be, in principle, unable to know which world we're in. And that's where the kind of indeterminacy of quantum mechanics comes in. It's in the way in which, looking only at the sense in which timelessly you're either in the left-hand world or the right-hand world, given divergence. But if you just look at the past, and that's the only evidence we typically have, then you're not going to be able to tell from the past whether you're in the left-hand or the right-hand world, because both the left-hand and the right-hand world have exactly the same past. So every information about the past isn't going to allow you to predict the future. So that's where the indeterminism of quantum mechanics is coming in this picture. So that's Lewis's argument in a nutshell. Splitting worlds lead to this problem with thought about the future, and with giving semantics for our language about the future. Maybe that's a thing of secondary importance. And divergence doesn't raise those problems. So Lewis, he didn't have any physics to go by. He was just kind of picking whichever metaphysical picture he wanted to do the metaphysical work he wanted to do. And so he chose divergence. He just kind of posited that all the possible worlds in his picture were divergent worlds. So there was no sharing of parts between them at all. And I'm going to argue that an Everettian can essentially do the same. Because this kind of choice between the overlapping and divergent interpretation of the formalism is one which isn't forced on us by the physics. So we can choose whichever is most convenient for helping to understand the physics. And in the project of reconciling our ordinary view of the world with the equation of quantum mechanics, I think the divergence metaphysics does a better job of affecting that reconciliation. It helps us to give better explanations of why we think and talk about the future in the way that we do, given what's going on in the physics and metaphysics. Okay, so that's the first way that I want to say that arguments for analytic metaphysics can help the Everettian project. they can give the Everettians reason to go for a diverging version of the many worlds picture rather than for a splitting worlds overlap version. Enough divergence and overlap for now. So the second way in which metaphysics has the potential to offer something to Everettians I'm going to talk about is to do with probability. So in a sense, that last issue was also to do with probability, because amongst the things we want to do to in our thought and talk about the future is to ascribe probabilities to future events. We want to say there's a 50% chance that the measurement will give spin up and a 50% chance it will give spin down. And one very prominent objection to many worlds proposal is that probability doesn't make sense in it. You might think that what Everettian quantum mechanics says is there will be a multiverse. There's going to be all of these worlds out there in there are all these worlds out there, and where they are is interesting question. There are all these worlds, and there are all those worlds with a probability of 1, because the linear unitary evolution is deterministic evolution. You put in one quantum state at the start, you get a single quantum state out the end. It's not an indeterministic rule. The only indeterminism only comes in with the Born rule and the collapse mechanism. And because Everettians deny there's any collapse mechanism, they're going to say there's no indeterminism in how the quantum state is going to evolve. So fundamentally, the world is deterministic. There's just a quantum state evolving deterministically. But nonetheless, they want to recover, they want to make sense of our talk about probabilities for experiments, for example. And also they want to make sense of our talk of chances more generally. So even the chance when you toss a coin, if quantum mechanics is a true fundamental theory, then the coin is a quantum object, and somewhere, if you trace it far back enough, I mean, maybe that it was determined by the way you tossed it to land the way it did, but far back enough, if you trace back, you'll find some quantum mechanical process, maybe in your brain, maybe even further back still, that determines which way the coin lands. So even coins are going to be quantum mechanically probabilistic in the end on this kind of picture. So all of our objective probabilities we want to make sense of. So how can we do that if with probability 1 there's going to be a whole multiverse? Well, so my suggestion is, again, we should borrow a page from David Lewis's book and think of probability as what I'm going to call an indexical phenomenon. So the probability of some outcome isn't that the probability of that outcome will exist full stop somewhere, because given that there's a multiverse, and that some world of the multiverse is going to have that outcome, with probability 1, it will exist somewhere. Rather, we should think of the subject matter of probabilities as being probabilities for specific worlds. So the probability that, the probability of spin-up, the half probability of spin-up is a half probability of spin-up occurring in my world. So probability stops being something that's occurring at the fundamental level of the wave function, and instead is something that occurs at the emergent level of worlds. So essentially, you can think of the probability of something as being the probability of being yourself in a world with that property. I've described it as relating to yourself. That's actually dispensable. The basic point is that probability should attach to individual worlds rather than to whole multiverses. And so this is a somewhat controversial way of trying to deal with the probability problem for Everettians. There are other ways of doing it. So Hilary Greaves, for example, has suggested that instead of, we should just give up probability altogether. She thinks that there's just no way to recover probability in an Everettian, non-trivial probabilities that aren't 1 or 0 in an Everettian picture. So we should just give up trying. It's impossible. Instead, we should try and reconceptualize our behavior or our ways of thinking on discovering that we live, or starting to believe that we live in a never-ending world. Instead of thinking about different outcomes having different probabilities, we should decide how much we care about different worlds. So a world with, she thinks we should interpret quantum mechanical amplitudes as a kind of caring measure. So a world with a high quantum mechanical amplitude, a high weight, normally thought of as high probability of being, of collapsing to that, is really just a world that exists just as much as any of the others, but one that we should care about more. And so it's part of quantum mechanics that we should just take the amplitudes on board as determining which worlds we should care about and to what proportions. So I think that's a really bizarre and major departure from our normal ways of thinking about different outcomes. I would like to try and find a way that is not as revisionary as that, and that preserves more of our ordinary ways of thinking. But David Wallace has another approach. He says we can keep probability. Probability is a useful word. Everything definitely are allowed to keep it. What they have to give up is the idea that probabilities, having non-trivial probabilities ascribed to outcomes, requires alternative possibilities, only one of which is actual, or genuine uncertainty as to what the outcome is. He writes, delete as applicable. So both these things seem true about probabilities. If there's a 0.5 chance of up and a 0.5 chance of down, then we have two alternative possibilities, up and down. Only one of which will be realized. And so that seems to go in the everything picture. And he says, or probability might seem to require genuine uncertainty as to what the outcome is going to be. And again, he says we don't have that in the everything picture because we can know for certain there's going to be multiple branches. So he said we should just give up these claims about probability. We've learned from quantum mechanics that probability doesn't in fact require alternative possibilities, only one of which is going to be realized. And it doesn't in fact require the possibility of genuine uncertainty about the outcome. We can just give up those conceptual connections between probability and uncertainty, and between probability and alternative possibilities. Now again, I think that's too radical a move. So maybe this is just me speaking as a metaphysician, but I think those connections between probability and uncertainty, probability and alternative possibilities are really, really central to the nature of probability. I think we're not really talking about probability anymore when we get rid of those. And he may be keeping the name, but really his approach is in the spirit of the Hilary Greaves caring measure approach. So I don't find either of those kind of revisionary approaches very attractive. But I want to try and recover almost everything we ordinarily believe about probability in my picture. So one of Wallace's principles was that probability requires alternative possibilities, only one of which is actualized. So only one of which is realized. I want to replace that with the thing I said first, that probability requires alternative possibilities, only one of which is actualized. And I want to make a distinction, following David Lewis, between what's real and what's actual. So these may sound, these sound pretty synonymous, and the dictionaries do often define them. But I think it's a useful technical term. We can usefully create technical terms by distinguishing them. And thinking of reality as just a kind of broader thing. Anything there is at all is real. But not everything there is actual. Actual means around here. It works in the same way as here or now does. What moment is now changes as time goes by. And in the same way, which world is actual varies from world to world. So this world, the one we're in, is actual for us. For all those people living in another world, that world is actual for them. So actual is working indexically. And then we can keep this connection between probability and uncertainty. It's just that probability is linked to uncertainty about what's going to be actual rather than about what's going to be real. And likewise, probability can still continue to require alternative possibilities, only one of which is actualized. But that's perfectly fine. That's compatible with everything in quantum mechanics. We do have many possibilities, many different worlds, only one of which is actualized, only one of which we're in. So my thought is that this approach, kind of inspired by the modal realism of David Lewis, is going to be able to reconcile our ordinary belief about probability with an Everettian many worlds approach. So I think actually once we start along that road, we can continue and do some more useful work. So Lewis used his possible worlds to analyse possibility and necessity. He said, what's possible is what's true at some possible world. What's necessary is what's true at all possible worlds. And my suggestion, this really is just me now, I'm not speaking for any of the other Oxford Everettians, is that we can give up on Lewis's logically possible worlds and make do with just the world of Everettian quantum mechanics and still use them to give a theory of possibility and necessity. So what's possible is what's true at some Everett world. What's necessary is what's true at all Everett worlds. So it's possible that the measurement should come out down because it comes out down at some world, even though it comes up at this world. And it's necessary that the laws of quantum mechanics hold, because the laws of quantum mechanics hold at all Everett worlds. That's philosophically controversial, because philosophers think the laws of nature are contingent. They could easily have been otherwise. I don't think there's any good reason for that assumption, actually. I think it's, it rests on bad metaphysics and bad epistemology of metaphysics, but I'm not going to argue about that now. But so if you do have this picture whereby the different Everett worlds comprise alternative possibilities, then that actually solves a philosophical problem about the nature of possibility. Possibility and necessity have always seemed odd to philosophers because they seem to go beyond just what is the case. We can look all we like at what is the case, and that might seem not to tell us about what is necessarily the case. But this version of modal realism that I'm suggesting we should combine with the Everettian approach makes possibility and necessity not mysterious. Possibility and necessity are just features of particular parts of reality. And they work in this indexical way. Actuality works in this indexical way, and using the kind of semantics that David Lewis offered for his version of modal realism, and what he called counterpart theory, which is, I should say something very quickly about counterpart theory. One consequence of divergence is that you and me are only in one world. All of us are in the same world. So that means that anybody in any other world is different from you or me. They're other people. They're numerically distinct in the terminology I was using earlier. So each of us exists in exactly one world. How then do we get it to be the case that instead of being a philosopher, I could have been a train driver? Because, so Lewis suggests, there are other people in other possible worlds, or in my version of it, there are other people in other Everett worlds, who are very like me in relevant ways. Maybe they came from parents that were very like my parents, and they have the genetic makeup that's very like mine. And in their world, they are a train driver. And so what it is for it to be the case that I could have been a train driver is there to be some guy just like me in some world who is a train driver. And so possibility is reduced entirely to what is the case. And that philosophers have often thought is a kind of holy grail. People haven't liked Lewis's way of doing that, because in order to achieve that theory of possibility and necessity, he posited continuum many worlds with every single world that was logically possible was part of this picture. So there were worlds where quantum mechanics failed, there were worlds that consisted of exactly one pink elephant and nothing else. And we're supposed to be able to know that all those worlds exist purely on the basis of reflection on the concept of possibility. Now, most people think that that's absurd. Obviously, reflecting on the concept of possibility can't demonstrate that all these worlds exist. And I'm not suggesting that it can. In my version of the many worlds approach, all of the worlds are worlds which we have reason to believe from quantum mechanics exist. So if you're an Everettian, you believe in all these worlds already. So you might as well use them to do work in philosophy, such as giving a theory of possibility and necessity. That might not sound much, but to philosophers interested in these things, that's been one of the hardest problems, accounting for possibility and necessity. So it's quite some progress if it turns out Everettians have an advantage in doing that over everybody else. So I started out by promising that I was going to give some ways in which analytic metaphysics can help Everettians. And I suggested that in making clear the availability of a diverging picture and showing its advantages, they could help Everettians to find better ways of explaining their own theory, better ways of formulating their own theory, in fact. And I also suggested that by thinking of the different Everett worlds as alternative possibilities, we can help with the problem of probability, which many people have taken to be fatal to Everett. I mean, the problem of probability shouldn't be underestimated. It's the kind of single most popular objection to the many world proposal. And I think that can be solved by using these considerations introduced by a metaphysician, David Lewis. So those two ways are ways in which metaphysics can help understanding quantum mechanics. But I finished by describing a way in which I think quantum mechanics can help with metaphysics. It can provide us with resources which we might not have known were available, with which to do our metaphysical theorizing. So we could give much better theories of possibility and necessity if we had all the Everett worlds on the table when we're trying to build our metaphysical theories than if we didn't have those things on the table. So the interaction here is helpful in both directions. I'm seeing metaphysics as having something to offer to philosophy of physics, but I'm also seeing philosophy of physics having something to offer to metaphysics. And the metaphysics is the kind of many philosophers are suspicious of metaphysics, and it's always had a bit of a hard time, it has to continually justify its existence. And that's with good reason, because metaphysical speculations can get way out of hand. But insofar as it can engage in both these directions with philosophy of physics, I think its epistemic credentials are significantly bolstered by being able to do that. So I'll just finish up by saying something about some remarks of Hamza's in his first talk. So he didn't go into the details of his problems with Everettian quantum mechanics, but I read that he thinks that the metaphysics is obscure and inflationary. And what I've been trying to do is try and clarify the metaphysics by suggesting we should think in terms of a parallel world picture rather than a splitted world picture, and by combining with probability in the way I suggested. He also suggested it leads to no new physics. Maybe that's a disadvantage to people that well, maybe that's a disadvantage. I think the other Everettians see that as an advantage. I don't think that interpreting quantum mechanics should lead you to new physics. We hope there will be new physics around the corner, but the guess of the Everettians and my guess is that new physics is going to come from understanding kind of the fundamental interactions and the dynamics, rather than fiddling with fundamental probability kinematics, which is really what Everett is. And if you'd like to come up, I might stop there.
very much for very interesting talk. So I appreciate these questions. I guess we will need lots of questions. Yes, please.
Thanks for that. I've got two questions, but I don't want to take up too much time, so maybe you can choose which one I should pose. One question about divergence specifically in Everett, or one about modal realism?
I think I'd be much better able to answer one modal realism, so I'll let you ask me that.
Okay. So here's analogous position to yours, which one could have formulated if classical physics had been in fact the theory we believe. We've got possible worlds given by worlds with the same laws of physics but alternative initial conditions. Now, how good or bad is the analogy? Do you see the Everett many worlds playing a more useful role metaphysically in the discussion of possibility and necessity than this classical analogy?
Okay, yeah, thanks. It's a good question. So I do think that it would be possible to get a kind of modal realism out of classical mechanics. Simply take all of the allowed histories given by a range of initial conditions and treat those as your possible worlds. And in fact, I think that would work out quite well as a theory of possibility. Again, it's controversial in that it would make the laws a necessary business, but I'm happy with that. And I think it would have the desirable result of giving an analysis of possibility and necessity in non-modal terms. So it would philosophically be a good theory. However, the epistemology of that theory would be dubious, because the only reason we would have to believe in all of the other classical worlds other than our own would be to help with our understanding of possibility and necessity. Now, that might be a good enough reason. If you're David Lewis, you might well think it's a good enough reason. I don't think it's a good enough reason. And I think the difference with Everett is that Everett gives us reason to believe in the kind of concrete physical reality of the other worlds. And so we kind of have them on the table. If we believe Everett, we have them on the table, and we might as well use them in our theory of modality. And so it's not that the theory is itself vastly better. I do think it actually might have some other advantages to do with the kind of causal relations between worlds and the kind of knowability. Well, actually, I'm not sure how that would relate to the classical case, so I won't say that. But the point is the theory of modality based on classical mechanics would be quite a good theory, but we wouldn't have the same kind of reason to believe it that we have to believe the theory of modality based on Everett if we're already Everettians.
So just a clarification on divergence. So let me use the term lefty to refer to the left branch in your divergence diagram. Now when I use the term...
When you say left branch,
on the
divergence diagram.
On the divergence, yeah. So lefty refers to the left side.
Yep.
And I use lefty, something like shorthand, to refer to the coordinate in possible world space to pick out that particular branch. Now, that seems to be a property I'm picking out that shows that they are qualitatively discernible.
Now, one is lefty and one is right.
Yeah. Now, what I want to do is put pressure on the idea that they can be indiscernible and yet be divergent.
Okay. So, what I'm saying is indiscernible is only that initial vertical segment. Obviously, they're discernible after they diverge. The divergence is kind of qualitative divergence, so they definitely become qualitatively different after that divergence point. It's just the first segment, the vertical part, that I would say is qualitatively discernible. And what you effectively suggested was that we could put a label on one and a label on the other, and then say, think of the property bearing that label as being a way of distinguishing them. Have I got you wrong?
I would probably use it loosely to refer to something as a coordinate in a possible world space. I wouldn't just be...
Well, in that case, I would want to say those coordinates are, again, labels. we don't have any reason to think those coordinates reflect anything beyond just our parameterization of the space. This is, here we've also made a distinction between the qualitative and the non-qualitative. There could be I want to say that bearing that label is a non-qualitative feature. So even though we can label the first vertical segment, the left vertical segment lefty and the right vertical segment righty, that's not a qualitative feature. And it's not corresponding to anything in reality, it's just a label we're using.
Okay, cool.
So this question, which I thought of independently, fits quite naturally with that last one, actually, but it's slightly more mathematically posed. So if I have a graph which is flat over a finite range, perfectly flat, and then ceases to be flat and starts wiggling around, at the point where it starts to wiggle, at least one of its derivatives must be singular. In view of that, I grant that this divergence is logically possible, but is it established that it can emerge from the sort of low-order differential evolution that you have in the Schrödinger equation?
Well, short answer, I don't think it is, no. And this is a really big open, this is what I see as the biggest open problem to the Everett picture, is making sense of, well, actually I think it's a problem whether what you're trying to do is getting an overlap picture or a divergence picture out. So, yeah, so this is a big problem, and David Wallace and some forms treated it at length with their philosophical discussion of decoherence. I'm not convinced they've resolved all the issues, actually. And this is the main reason that I remain I'm not entirely convinced by it. I think it's the best theory we've got at the moment, but I'm not 100% convinced by it for these sorts of reasons. And I'm not going to be able to say anything kind of in defense of the Everettians here right now. But I would say, yes, these things are only approximately defined. Everettians say things like that. They're only approximately defined. And one of the weirdest things they say about them is that these histories are indeterminate in number. There's no fact of the matter about how many there are. And they say, well, that's a general feature of higher level ontology. So if you try and count clouds, there may be no fact of the matter about how many clouds there are. There are obviously big differences between clouds and worlds. It's unclear how much weight that analogy can bear. But so yes, I'll just leave it and say there is a significant open issue with everything quantum mechanics here, and it's not what I'm trying to address today.
I'm wondering how you respond to the old standard point in philosophy of science that any theory to counter-scientific must be testable by some conceivable observation. If we postulate many worlds or universes, as you're clearly doing, all of them are physically real. They contain the matter, energy, maybe even some intelligent people, but they're causally isolated. No signal, energy, or information can be transmitted from one to the other. Therefore, there can never be any evidence of their existence. Therefore, whatever virtues Everettian metaphysics may have, they don't have the virtue of being scientific.
So, yeah, there's lots and lots of things to try and say to that. I'll start by saying I think that would be a good argument against, for example, David Lewis's modal realism. I don't think we could ever have any scientific reason to believe in those other worlds, because they are ex-hypothesi, based on horror and causally isolated from one another. These worlds are approximately causally isolated from one another, and I've been talking as though I've been kind of neglecting the approximately, but there are in principle some small, perhaps usually negligible interactions between the worlds the decoherence conditions are that the interference between the worlds should become negligible for all practical purposes, not that they should vanish altogether. But there may be, I mean, for reasons to do with analysis of causation, I might well actually want, and this is now my view, I want to think of causation as something that occurs within worlds rather than between them. I don't think there's any causation at the fundamental level. I think causation is quite a high-level concept that only occurs within the world, in which case there is no causation between these worlds. Nonetheless, I'd like to use the analogy of a jigsaw puzzle, in the sense in which if you have a jigsaw puzzle and you take a piece away, the other pieces around the whole haven't caused the missing piece to be the shape it is, but nonetheless they do provide some kind of non-causal explanation for it being the shape it is. It has to be the shape it is if it's to fit into that hole. In the same way, if you took one of these diverging histories, or even overlapping histories, it doesn't matter for this sake of argument, if you took one of them away, there would be a gap left in the picture. So I think there may be kind of non-causal explanations of why we need the other world, even if we don't think there are causal explanations of why we need them.
Just curious to ask, in any one Everett world, are past, present and future distinguishable? And the reason I ask that is that our common sense intuition is that the future is open, and so there's some kind of possibility. But if I've understood you correctly, in the divergence model of Everett worlds, everything is actual, and therefore past, present and future are all the same. Is that true?
So suppose we're in one of the diverging worlds. Yes, the whole history is actual. I don't take actual to mean actual and now, actual present. Actual applies to all of the states of the world. So some of the actual states, some of the states of the actual world are past states, some of the states of the actual world are future states. I mean, this is a kind of B-theoretic picture, and so the sense in which these are histories laid out through time, and they're there timelessly. I would try and capture the openness of the future, but I don't want to capture it in I don't want to give a metaphysically strong reading of openness. I want to give a kind of epistemic reading of openness. So, if you're in one of these diverging histories, you can inspect the past. In principle, you could know everything there is to know about the past. But even if you knew everything there was to know about the past, you still wouldn't be able to predict the future, because you wouldn't know which of the many histories with indiscernible pasts you're in. So there's going to be an epistemic asymmetry between past and future. And whether you want to say that unacceptably the future is not open in some way depends on what you think openness amounts to. And I'm not convinced that there needs to be some strong metaphysical sense in which the future is open that isn't given by this picture. But this is a big debate in philosophy of time, and this is just one instance of a theory that is B-theoretic in that sense.
Is there any other? Oh, yes,
Hello, my name is Stephen Gamble. I was just thinking through the consequences of your two world models there, the overlap and the divergent one. In the overlap one, you're continually creating new worlds, it seems to me. So the number of worlds starts at base 1 and is continually increasing very fast. In the divergent one, there's always the same number of worlds. So at the very start of time, when there are all these many worlds, what mechanism is there for knowing how many worlds are going to be? Because surely that's determined by something that's happening in the future. So how did all those worlds come to being, given that the thing that creates hasn't happened yet?
Yeah, I get the question. It's a good question. The sense in which at the start of time the quantum state does know what it's going to be. So the state as a whole, because that evolves deterministically, if you fix a state at the start of time, you've thereby fixed the state throughout time. So the state itself does have all the information in it to kind of describe how many words you're going to need to use to describe it properly. I agree there's something funny going on here. It's not, we can't give some kind of, we don't have the kind of mechanical image of world creation that we have on the left-hand side. And so there's a sense of preordination about how many words there are going to be. I think that's something Everettian should just live with and lean again on this favourite tool of the Oxford Everettian, the distinction between the fundamental level and the emergent level, and say, well, these worlds are just emergent anyway, they're not fundamental. So it doesn't really matter because the laws that govern how many of them are not fundamental.
I have a brief worry about the puzzle picture, which is very nice at first sight, but I wondered, so if you take out one of the divergent worlds out of the picture, there's a piece missing, which has to have this shape, right? That's the energy used. But what is that piece missing in? I mean, it's not missing in the actual world, right? It's missing in the multiverse picture. So there cannot be any evidence in the actual world for the missing piece. The evidence comes from already being an Everettian, of already having the view of the multiverse, right? So you're walking in a circle, I suspect.
Yeah.
Except if there is something in the actual world which would be different, were that other not to be existing.
I think it's okay to appeal to features of the Everettian worldview in defending the thing from an Everettian perspective. I mean, this is meant to be a defense against an objection to Everett rather than an argument for Everett. And it's fine to appeal to other things Everettians believe in defending their view. So I think that's all that's going on. I would say that considering this possibility, taking it seriously, the possibility of one of them being missing, is a kind of it's a conceptual toy, but we shouldn't think of it as reflecting genuine possibility. Because if everything I've said is true, then it's actually absolutely necessary in the strongest sense, that all of the worlds that in fact exist should exist. The whole multiverse is non-contingent on this view. So it's not a genuine possibility to take a world out. We can do it in thought, but we should bear in mind that that's all we're doing when we do it.
If you are agree, we can have for one more question, and that's the last question. So, okay, probably you was first.
Well, can I just say thanks for giving it a go. I've always wondered, struggled even to make sense of the interpretation. So I just take my hat off to you as someone who's just even trying to make sense of this metaphysics. So thank you. You started off by saying it's the sort of most conservative regarding the science. I'm wondering, that comes up in identity and probability. On the principle of identity of indiscernibles, you seem to be saying the way to identify things is indexical, if I've understood you right.
No. Identity is meant to be a kind of a given thing. Everything's identical to itself and it's not identical to anything else.
Yeah, that's my point. So if, in what sense then is, you refer to possibility as other possible worlds in which there's enough similarity to me. In what sense can it be meaningfully like me?
They're meaningfully like you in that they have similar qualities. So they might be your height, they might have your genetic code, they might even have had a life which is indistinguishable from yours in every way, right up to 2 seconds ago, before some quantum mechanical events in your brain went slightly differently. These people could be very, very, very like us. Such if you watched a video of them, you'd think they were you.
Well, you wouldn't, because what you're saying is what marks these things out is precisely their hints. So,
sorry, indexical doesn't mean identified via an index or via a label. It means I'm not sure how to explain indexical without giving examples. Indexical just means a term which works like here, in that it varies, what it means varies from context to context,
Sure.
user to user.
But then the problem is, what is meaning like here? Nothing is. So the relationship breaks down as far as I don't see how you can guard meaningful transworldity or transworld comparison, and then
Comparisons are all purely qualitative. So all in terms of qualitative resemblance. Now we understand qualitative resemblance between people. You know, I resemble you more than I resemble a one-year-old baby.
Yeah, within the world.
Yes, and I don't see any problem with extending those comparisons into other worlds, given that I think other worlds are just more of the same. The only difference is that they're space-temporally isolated from ours. They just don't stand in any space-temporal relations to us, but in every other respect, they are qualitatively the same.
That's a pretty big step.
Well, yes and no. I mean, it's just more of the same. It's just not any relation, not any spatial relation to him, or temporal relation to him. That's enough.